Okay, so let's take a look at some of the different kinds of equations that could involve having the exponent, or sorry, having the variable in the exponent, or having the variable in the log. And again, some of this might be familiar, so feel free to like scroll through the video just to the problem that you may have gotten stuck on. So a couple of the examples try to get the bases the same. If the bases are the same, then the exponents have to equal each other. So I'm going to rewrite 16 as a power of 2. 2 to the x equals 2 to the 4th, but that's already raised to the x plus 2. I can multiply those as one of our properties. So now I have 2 to the x is equal to 2 to the 4x plus 8. And the thing is that when you have the same base, like when they're both base 2, that means the exponents have to equal each other. So you're not really dividing by 2, you're not necessarily needing to introduce a log here, just set the exponents equal to each other. Set x equal to 4x plus 8 and solve. So we get negative 3x is equal to 8, or x is equal to negative 8/3. Okay, that looks better. The next example, I'm noticing I could write things as powers of 3. 1/9 is like the reciprocal of 9 squared, and that reciprocal is a negative exponent. So I could definitely think of this as 3 to the negative 2. 27 is 3 cubed, but that's already raised to the negative x plus 4 power. And again, as soon as you have the same base, 3, that means the exponents must equal each other. And that's where I can derive an equation. So negative 2 is equal to, if I distribute, I hope I did this carefully, negative 3x plus 12. So I subtract, so I get negative 14 equals negative 3x, or x is equal to 14/3. Okay. And on the number 3, don't be intimidated that there's an e. That's the base, and it's already e and e. So I can just set the exponents equal to each other. X squared plus 8x must equal, if I distribute that, 6x. And so then I can subtract x squared plus 2x is equal to 0. Yeah, don't divide by x because you would lose a solution. We can factor. And so then that's true when x is 0 or x is negative 2. Okay, now the next example, back to powers of 3. 9 is 3 squared, but it's already raised to the 2x power. 27 is 3 cubed. It's already raised to the x squared power, and then 3 is already to the negative 1. So remember this property, when the bases are the same, you're adding the exponents. So this would have been, we'll go just a little bit further on the marker, 3 to the 4x plus 3x squared, because when you're multiplying the bases, you add up the exponents. So that's 4x plus 3x squared is equal to 3 to the negative 1. And again, bases are 3, therefore the exponents have to have an equivalent value as well. So I could say, okay, 4x plus 3x squared is equal to negative 1, or 3x squared plus 4x plus 1 is equal to 0. If I factor that, hopefully it factors. Otherwise, we know completing the square. So 3x and x, it looks like if I would do a plus 1, that's going to give me the solution of 4 in the middle. It's equal to 0. So then my solutions are x is equal to negative 1, or x is equal to negative 1/3. Okay, now number 5 isn't really, it's not necessarily necessary, that's kind of redundant, to actually log things. You can also just manipulate. Like here's your given statement, 4 to the x equals 6. If I can somehow manipulate this side to be 2 to the negative x, and keep track of all my operations on the right as well, as I'm doing them on the left, then I will be able to transform this into a 2 to the negative x, and therefore that would transform 6 into the desired outcome. So the first thing I might recognize is 4 is 2 squared, so that's 2 to the 2x. So I really haven't done anything. And I can kind of think about, well, 2 to the 2x is the same thing as 2 to the x squared, right? Because one of our properties, if you have an exponent to an exponent, you would have multiplied. So I'm kind of just undoing that. Okay, so I'm close. I have 2 to the x, but I want 2 to the negative x. So I'm going to introduce the negative 1 power. I'm going to put a negative 1 power to here, but here's where I'm going to also have to introduce a negative 1 power here. So I have 2 to the negative x squared is equal to 6 to the negative 1. In other words, like I'm basically introducing the negative 1 power. I'm introducing the negative 1 power. And it's all multiplication, so the negative 1 times x, there's your negative x squared, and then there's your negative 1. This is good. So then, now, how do I get rid of this squared? I'm going to do the 1/2 power. If I introduce the 1/2 power, maybe I'll use, green, but I want to go with that color. So now if I do the 1/2 power, that 1/2 power times 2 would cancel. So that would give me 2 to the negative x is equal to 6 to the negative 1/2 power. Because 1/2 times negative 1 is negative half. Now you could leave it like this, or we should be comfortable knowing that the negative half, like that would be like 1/6 to the half, and the half power is just a root, so 1/√6. You could leave it like that, you could rationalize it, so that's equal to √6/6. So really any of those would be acceptable in terms of the value, okay? Same idea with number 6, you're manipulating 25 to the x, and I notice right away it's a power of 5. So I'm thinking of 25, that's 5 to the 2x is equal to 27, or 5 to the x squared is equal to 27. And I could maybe do this all in one shot. I am trying to get 5 to the negative 3x, which I have 5 to the x here. I basically need to get rid of this 2 and introduce the negative 3. So if I raise this to a power, or that's a 2x, so if I raise this like to the negative 3/2 power, which I just realized is really hard to see. Let's try that again. If I raise that to the negative 3/2 power, negative 3 times 2x will give me negative 3x. So I'm going to raise this side also to the negative 3/2 power. So that gives me 5 to the negative 3x, which is I'm looking for. This is 27 to the negative 3/2 power. Now, 27 to the negative 3/2 power is technically the right answer. I, however, should be familiar and comfortable with knowing how do I manipulate this. And again, the negative is a reciprocal, and so I could think of this as 1/27 to the negative 3/2 power. 1/27 to the 3/2 power. And remember, we already said this is the square root, so it's the square root of 27, and that just means it's cubed. So I could have 1 the square root of 27, and I'm going to cube that. Well, cubing it means take it times itself. Well, 3 times. So √27, √27, and √27. I have got 3 √27s. 2 of them are going to cancel. So into just a normal 27. And then I'm left with that √27 there. And we might as well simplify that because that's 9 times 3. So there's a square root of perfect square that can come out. So I get 1/27 times 3 √3. And then that's 81 √3. And then I could also rationalize that. So kind of a little roadmap here. 1/81 √3 times √3/√3. So then I feel like this is exactly backwards in terms of working left to right. √3, and then that would be a 243.